right? So consider this situation. You can see that there is one bubble inside another bubble, which is exposed to air. Okay. So the pressure outside is atmospheric pressure. Take it as P naught. Fine. There's one. Okay. These are hemispherical bubbles. That's fine. Assume surface tension is T, and let's say radius of curvature of the bigger bubble is 3r, and that of the smaller bubble, which is inside, is r. Okay. So what I want you to find out is pressure P1 and pressure P2. Okay. The pressure outside is atmospheric pressure P naught, that is given to you. Surface tension T is given, and the radii of curvature of these bubbles is also given. Okay, are also given. Derive expressions for P1 and P2. Try this, both of you. I'll give you 2 minutes. One of you tell me, what is the formula for excess pressure across one liquid surface? Basic formula for excess pressure across one spherical surface.
So 2T by R.
2t divided by the radius. Okay. If there are two surfaces, then it is double of this 4t by r. Okay. Now what you have here, or what you're given here, are soap bubbles. And soap bubble has two surfaces. Fine. One on the outside, one on the inside. So across the first bubble, fine. First one, I'll just highlight it in red. This one, the outer bubble, I should say. Its radius of curvature is given 3r. Then the excess pressure across that. We discussed yesterday that the concave side will be at a higher pressure than the convex side. So P1 will be more than P naught. Okay. So excess pressure will be written as P1 minus P naught. And that will be, since there are two surfaces, one on the inside, one on the outside, you'll have to use the formula 4t by r. 4t divided by its radius is 3r. That's all. Therefore, the pressure P1 will be P naught plus 4t by 3r. Simple. Next, the second bubble, if you consider, which is inside the first bubble, its radius of curvature is r, and the pressure inside it is P2, the pressure outside it is P1. That second bubble is not exposed to atmosphere. Okay. So excess pressure in the second bubble will be written as P2 minus P1, and that will be equal to, second bubble also has two surfaces. Fine. So 4t divided by its radius. Its radius is r. Okay. So the pressure inside the second bubble, inside the inner bubble, will be P1 plus 4t by r. P1 is P naught plus 4t by 3r. So this becomes P naught plus 4t by 3r plus 4t by r. That can be written as 12t by 3r, which effectively becomes P naught plus 16t by 3r. Correct. So that's the pressure inside the second bubble. Fine. So remember, soap bubble, which has air inside and outside, has two surfaces. Okay, it looks like one layer only, but liquid molecules are exposed to air on the inside and also on the outside. So that one layer itself has two surfaces. So we have to use the formula 4t by r. Okay, good. Next, see how much a surface curves or bulges depends on the excess pressure across it. Okay, that is what this formula also suggests. Excess pressure is inversely proportional to radius of curvature. So greater the excess pressure, smaller the radius of curvature. Fine. So consider a situation like this. You may have seen bubbles coming into contact with each other. Okay, one bubble touching another bubble. Now, when two bubbles come into contact with each other, it's not necessary that they merge and become a single bubble. They will stay separate as two bubbles. In this picture, let's consider this one as one bubble, the one I'm highlighting in green. Consider that as one bubble. It has its own radius of curvature. Let's say its radius of curvature is R1. Okay. And then consider this one, the bigger one. It has its own radius of curvature. Let's call it as R2. Now these two bubbles are touching each other, one bubble on another bubble. Let's say this one's radius of curvature is R2. Outside, there is atmosphere, so the pressure outside is atmospheric pressure. Depending on the radii of curvature, you can find out what is the pressure inside. So you can tell how much is the pressure P1 inside the first bubble. You can tell how much is the pressure P2 inside the second bubble also, depending on their radii. Okay. But you see, the common surface that they share, okay, that these two bubbles, 1 and 2, they share a common surface. That common surface, if you observe carefully, seems to be having a different radius of curvature altogether. Okay, let me mark that in orange. It's like this. It's not equal to R1. It's not equal to R2 also. And if you can observe, I mean, if you observe carefully, that common surface between the two bubbles is concave on the left side, convex on the right side. Okay. Uh, Fine. Let me use a different color to highlight that common surface. Okay. This one, it is concave on the left side, convex on the right side. Usually the concave side is the side where the pressure is higher. Okay. So how much it curves depends on the pressure difference. It depends on P1 minus P2. Okay. So in this question, assume R1 is given to you, R2 is given to you. You know the pressure outside is P naught. Okay. So I want you all to derive the radius of curvature of the common surface of the two bubbles. Okay. Try this, both of you. I'll give you all 2 minutes. Did you understand the situation? If you have any doubts, you can ask. Otherwise, start solving the problem. Right. So the problem here is to calculate the radius of curvature of the common surface. Fine. So you need to remember that radius of curvature of a surface depends on the pressure difference across the surface. So you first need to find out the excess pressure across it. Okay, that common surface has pressure P1 on one side, that is the pressure inside the smaller bubble, and pressure P2 on the other side, pressure inside the bigger bubble. Let's say these two bubbles are made of the same liquid which has surface tension T. Okay, I must have mentioned that, I didn't. Fine. So we first need to find out the difference between P1 and P2. If you know that, then you can tell the radius of curvature of the common surface. Okay. Then we'll have to write expressions for P1 and P2. P1 is the pressure inside the first bubble. Pressure outside is P naught. Pressure outside any of these bubbles is P naught. Okay. So for the first bubble, excess pressure would be written as P1 minus P naught. Okay. Pressure inside the bubble will be greater than pressure outside. So we write the excess pressure as P1 minus P naught. And bubble, as I said, it has two surfaces. Outside it is exposed to air. Inside also there is air. So two surfaces. Therefore, the formula becomes 4T divided by R1. That's the radius of curvature of the first bubble. So you get P1, pressure inside the first bubble is P naught plus 4T by R1. Similarly, excess pressure in the second bubble, which is P2 minus P naught, will be 4T divided by radius of the second bubble. So pressure inside the second bubble would be P naught plus 4T divided by R2. Okay. Now we want radius of curvature of the common surface, which depends on pressure difference across the common surface. On the left side of the common surface, the pressure is P1, and on the right side, the pressure is P2. And P1 will be greater than P2. How can I say that? Greater the pressure in the bubble, smaller will be its radius. Okay, because excess pressure is inversely proportional to radius. No, based on that, I'm telling. So P1 will be greater than P2. And based on this curvature, also, you can tell the common surface is bulging to the right side, means the left side pressure is more. Okay, that is when it bulges to the right side. Okay. So to find radius of curvature of the common surface, we need excess pressure across it, which is P1 minus P2. And if you subtract these two, P1, P2, you'll be left with 40 into 1 by R1 minus 1 by R2. Okay, that's the excess pressure across the common surface. Now the common surface also, that layer that I have highlighted in white, it has two surfaces. Okay, I've been calling it a common surface, but I should have called it a common layer, fine, between the two bubbles. It has air on the left side, it has air on the right side also. So there are two surfaces to it. So you will need to equate this. We got an expression for excess pressure. Excess pressure across two surfaces is 4T divided by the radius of curvature of that surface. 4T gets cancelled. Therefore, 1 by radius of curvature of the common surface is 1 by R1 minus 1 by R2. Okay. If you take LCM and simplify, you get radius of curvature of the common surface as R1 R2 divided by R2 minus R1. Okay. The idea here is that radius of curvature depends on excess pressure across it. Okay. Next, just a moment, I'll draw one diagram. Okay. Uh, Assume there is a straw on the ends of which two bubbles are formed. Okay. Both bubbles are formed from the same liquid. The liquid surface tension is T. Okay. Actual value doesn't even matter. You can see that there are two bubbles formed, one on the left side, one on the right side. Let's name them as A and B. In between, there is a stopper. Fine. They are formed from the same liquid. Keep that point in mind. The straw is open. In between, there is a stopper. So stopper doesn't allow air movement from one side to the other side. So the question here is, if the stopper is removed, fine. Stopper means you assume the straw is clamped, not allowing airflow from one side to the other side. Now, if you remove that clamp, okay, let's say some clip was placed, remove the clip. What will happen is the question. I mean, there are two bubbles A and B. They are of different sizes, obviously, as you can see. Which bubble will become bigger, which bubble will become smaller, and what will be the final situation? Okay, that is what I want you to think about. So what happens after the clamp is removed? Okay, think about it carefully. I'll give you 2 minutes. First, tell me, why do you think air moves from B to A?
So pressure inside B is more, so
Okay,
air will go from high pressure
right.
to low pressure.
For both the bubbles, outside pressure is P naught. Pressure inside depends on the radius of curvature. We know excess pressure is inversely proportional to radius. B has a smaller radius. That means it has higher excess pressure. So pressure in B, let's call it PB, will be greater than pressure in A. And when you allow free flow of fluid, it flows from high pressure to low pressure. So air flows from B to A after the stopper is removed. Okay, that is correct. Now, as air flows from B to A, the size of the bubble B will decrease, size of the bubble A will increase. Okay. Now, till when will this airflow keep happening? Generally, fluid will flow as long as there is a pressure difference, right? So suppose the stopper is removed and we know the direction in which air flows. So size of B decreases, size of A increases. Now, size of B decreases, does that mean pressure in B is increasing? Suppose A has become bigger like this, fine, and B has become smaller. Becoming smaller means what? Radius decreasing. Radius decreasing means pressure increasing. Then that will lead to more and more airflow from B to A. Finally, what will happen is, see, airflow stops, generally fluid flow stops when there is same pressure on both sides. Okay. How can there ever be same pressure on both sides is the question here. Because radius of B is smaller than A and air is going from B. So B becomes even smaller. Then how can the pressure ever become same? See, as B becomes smaller and smaller, if you take a side view of the straw, if you visualize the side view of the straw, On one side, you have the bubble A, okay, which has become bigger, let it be. On the other side, see the bubble A has a certain radius of curvature. Okay, I think it'll be better if I draw a proper circle. Just give me a moment. Because I'll have to cut out a part of it. Okay, this is the bubble A on one side. On the other side, B has become smaller and smaller. The question is, how can pressures finally become equal on the both side, on both the sides? Any guesses, anyone? Okay. If you observe, there is this part missing from the bubble A. Okay, this will be open space here. The part that I'm marking in orange will be open space. Okay, open into the straw. You will see that on this side. That is what bubble B finally reduces into. Okay, such that the radius of curvature on both sides is equal. Okay, what I mean is on the right side also, if you allowed it to be a full bubble, it would have looked like this. Okay, so the radius of curvature on both sides has effectively become same. On one side, you'll see it as a proper bubble. On the other side, you'll only see a small part of the bubble. This is what finally happens. Okay, A becomes bigger, B becomes smaller. But finally, the radii of curvature become equal. Keep that point in mind. I mean, I'm not asking you to memorize it, but I hope you understood what happens here. Only when the radii are same, the pressures are same, and the airflow will stop. This is what the final state will look like. Okay. Next question. Okay. Assume there's a glass tube bent like this and there is liquid in it. Fine. In between, there is a tap also, as you can see. Okay. There's a valve basically, which as of now is not allowing the flow of liquid from one side to the other side. On the left side, you can see a small liquid drop hanging. Okay. Which I have highlighted in orange. On the right side also, there is a small liquid drop hanging, which I have highlighted in green. Okay. Hope it is clear. Like by looking at them, you can get an idea of radius of curvature and all. So I want you to find out if the valve is opened, from which side to which side will the liquid flow? Okay, think carefully. If the valve is opened, from which side of the tube to which side of the tube will liquid flow, if any? Okay, we need to decide from which side of the valve to which side of the valve the liquid is going to flow. So we have to find out on which side the pressure is higher. Okay, so call this point as X and this point as Y. We need to find out the pressures, or we need to find out which point out of these two is at higher pressure. Okay. Can any of you tell me how to comment on the pressures at X and Y?
So we can find out the pressure at the end.
Okay. So she is like when I saying we'll find out the pressure here. Let's call this point as A and this point as B. Based on the pressures at A and B, we can tell the pressures at X and Y. Correct. Uh, Now, can any of you comment on pressure at A and pressure at B? Which pressure is greater?
So PB is greater.
Correct. But why? Why is PB greater than PA?
Sir, because the radius of curvature is less for B.
Good, good. See, at both ends of the tube, there are drops hanging. Okay. If you look at B, the drop hanging there has a smaller radius of curvature. It's like this. If you imagine the full sphere, the radius of curvature is like this. At A, if you imagine it as part of a sphere, the sphere would be like this, bigger. Okay. So the surface of the drop which is hanging at B has a smaller radius of curvature than the surface of drop hanging at A. And smaller radius of curvature means more pressure inside. Outside, the pressure is P naught for both of them. So pressure inside will be greater at B than at A. PB is greater than PA. And if PB is greater than PA, see this height and this height are equal. Okay. Pressure at Y will be pressure at B minus rho GH. Pressure at X will be pressure at A minus rho GH. The heights are equal. So rho GH term will be equal for both of them. So out of PA and PB, whichever is greater, based on that you can tell which pressure is greater between X and Y. And we know PB is more than PA, therefore PY is more than PX. That's all. Therefore, if the valve is opened, the liquid is going to flow to the left from Y to X. Now, if that happens, what happens to the drops that are hanging? Okay. Now, if you observe, the drop hanging on the left side is smaller than the drop hanging on the right side. Now, liquid is going to flow from right to left. As a result, one's size will decrease, two's size will increase, and they will become equal like this on both sides. So it's kind of opposite to what we see in case of air bubbles. Okay, these are drops. Fine. I mean, I don't want you to remember it like drops behave opposite to bubbles, but the answer here is opposite to the answer that we saw in the previous case. Fine. This question with air, like the question that I had pasted here was given in JEE Advanced 2008, the year in which I had written the exam. So I remember this question forever. Fine. Next, just a moment. Let me get another question. Okay. One relatively easy question. Try to answer this, all of you. Let's see. So an air bubble of radius 0.1 centimeter lies at a depth 20 centimeters below the free surface of a liquid. Liquid density is given 1000. So it's like water. Okay. Pressure inside the bubble is this much greater than atmospheric pressure. Then how much is the surface tension of the liquid? Okay. Need to be very careful with such questions. Let's first visualize the situation. The bubble is 20 centimeters below the free surface. Okay. Let's assume this is the bubble. Okay. Inside the bubble, let's call the pressure as P, and pressure just outside the bubble, let's call it as Py, pressure at a certain depth, and atmospheric pressure, let's take it as P naught. Now they said that pressure inside the bubble is 2100 Newton per meter square greater than atmospheric pressure. So pressure inside the bubble is P naught plus 2100 pascals. Okay. They're all in SI unit, so I'm not writing the unit. They have given the bubble's radius and they have given the depth also. Okay. We need surface tension of the liquid. Fine. How are all these related? Obviously through excess pressure. Radius, pressure difference, surface tension. These three are related through excess pressure. So for this bubble, this is a trick question actually. It's a bubble, that's fine, but the bubble is inside liquid. So inside the bubble there is air. Outside the bubble there is liquid itself. So there is only one surface in this case. Although it's a bubble, there's only one surface. And for one surface, the excess pressure is 2T divided by R. How do we write excess pressure in this case? Pressure inside the bubble, which is P naught plus 2100 minus pressure just outside the bubble. Pressure outside the bubble is not atmospheric pressure. It's pressure at a certain depth. How do we express that? P naught plus rho g y. Rho is 10 power 3, g is 10. The depth is 20 centimeters. That means 0.2 meters. That's the pressure outside. So this is pressure inside the bubble. This is pressure outside the bubble. So this becomes excess pressure, and we need to equate that to 2T by R. Okay, you have to observe how carefully you need to write the equations, how you have to consider everything when you apply an equation. Okay, P naught is going to get cancelled anyway. So you get 2100 minus 0.2 into 10 is 2, 2 into 10 power 3 is 2000. Okay, this is all in SI units. Should be equal to 2T divided by radius of the bubble. Radius of the bubble is given 0.1 centimeter. That is 0.1 into 10 power minus 2 meters. From there, you will get surface tension in SI units. They have asked the answer in SI units. Therefore, 2T becomes 100 into 0.1 into 10 power minus 2. These two cancel 0.1. Therefore, surface tension becomes 0.1 divided by 2. That is 0.05 Newton per meter. Good. Okay. This question was given in JEE mains this year. Okay. The exam that happened few days back. Is this clear? Any doubt in this? Fine. Okay. We'll stop it here for today. Next class will be tomorrow itself. Tomorrow I'll take from maybe 8 to 9:30. Okay. And tomorrow's class will solve some more problems based on surface tension and then move on to the next concept, which is capillary rise. Okay. Capillary rise happens due to surface tension of a liquid. That is also a very important concept for exam from exam point of view. We'll discuss that. We'll finish off. After that, we'll discuss viscosity. Okay. Thank you all. We'll continue tomorrow.
Thank you, sir.